However, an effective theory is quite useful, and it can be applied to phenomena as varied as, say, the world of quarks or the work we did with the oscillating diamond. And when we apply the effective theory to our work with the diamond, we imagine that the wires behave like rigid rods. In reality, the wires would behave like sine curves. And we would consider low frequencies to very high frequencies. However, at low frequencies, which we are choosing to consider with our effective theory, the wires would just barely be a sine curve. They would almost behave like a completely straight line. So therefore, we consider the wires to be rigid. Now, this has some significant implications for the work that we did, the theoretical work. And this is just a diagram of that. This is how the actual system would behave, but this is how we imagine it in effective theory. If we're looking at the diamond side on and imagining that it's oscillating along the z-axis. And one of the effects it would have is, well, if we imagine the rotation about the z-axis, i.e. when the diamond is rotating within its plane, and this corner will come down and then come back up, and this sort of motion requires stretching of the wires. Now, if we consider the wires to be rigid, this is a problem because you can't really stretch a rigid rod. Therefore, we can completely disregard this mode of oscillation when we consider our effective theory. And if you notice, the first order mode, or the first order frequency for this mode was very high when I showed you that slide before. And as I said, we're considering only low frequencies. So obviously we would remove this mode of oscillation in our effective theory. Now, it will also have an effect on our calculations. And here you see the equation for oscillation along the z-axis, the frequency being omega. And obviously this is a pretty complex equation that requires using the graph to find the intercepts, to find the solutions. However, in effective theory, we would not need the cotangent function. And the reason we include a trigonometric function is to account for the fact that the wire behaves like a sine curve. Now, if we consider the wire to be rigid, then we will remove the cotangent, and our equation will become much simpler. Now, this sort of highlights the steps that the equation goes through. And as you can see, this is a much simpler equation to work with than this. However, if you also notice, this has an infinite number of solutions, whereas this only has one. And the solution that this provides will be that lowest order frequency. In other words, the lowest frequency that the system can vibrate at. However, it provides very good results. Now, this is the result that we got using our more comprehensive equation in the graph. And it's 45.11 hertz, hertz being the number of oscillations in 1 second. And I did a little calculation using the effective theory equation, and I got 45.07 hertz. So as you can see, while we use an effective theory, we lose the power to predict higher frequency motions or higher energy motions, but we do get very valid results for low energy motions or low frequency motions. So it's a start. And we can sort of use effective theory as a foothold to learn about more complex theories. Now, this applies directly to GlueX because the world of quarks is very, very complicated. And when we discussed the diamond and tungsten wire system, Austin did show you some very complex mathematics, but it's in the realm of possibility to calculate those. It's actually fairly simple compared to what you would do when you're considering quarks. So we don't really need an effective theory in that case, but I provided those examples to highlight what an effective theory would look like. However, when you're discussing interactions between quarks and the gluons in the, say, a proton, you need an effective theory because we don't have the power at the moment to explain these in a more comprehensive way. Now, even the effective theory, which Ryan discussed, the standard model, I should say, is an effective theory. And so when we consider the work being done on the GlueX project, if it's successful, it will contribute to an effective theory of the interactions between quarks via the color force. And hopefully this will give us a foothold to come up with the more complex equations and models and such. However, what I think is very cool about considering effective theory in this way is that obviously considering the motion of, say, a diamond suspended on straight wires is vastly different than studying quarks. However, you see the basic methodology of science at work, and we can tie it all together in sort of this way. We have a basic methodology, as I said, that applies really in all areas of physics, and I think that's actually pretty cool. And that's all for my presentation. And sorry, I'd like to thank some people. Dr. Richard Jones for being my mentor. He helped us out a lot through the weeks, and it was very cool to work with him. And all the students that we work with in this lab, including Igor, Woody, and Chris, who are here, and also Mike, who's on sometimes. And it was good working with my fellow physics students, Ryan and Austin, because I think they probably knew a little bit more about physics and calculus than me, but I got to learn a lot. And all of the Mentor Connection staff and students, I had a great time in this program. And here are my sources, and that is about it. Are there any questions? Jeremy?
So, if the goal of this was like trying to minimize the frequency, the rotation of the diamond plate, right?
Well,
so like what degree of accuracy do you need?
Okay. Well, basically what we're studying right now is what frequencies that the diamond is oscillating at. And at least if we get a rough idea, that'll help us out a lot. And what we might actually do is increase the frequency of motion. Now, that may seem like it would make the problem worse. However, if you increase the frequency, then the amplitude of motion goes down. So, say, if it's moving slowly, it'll displace this much. If it's at a higher frequency, it might move like that. Therefore, the effect of being at different angles will be minimized, and that's how we might address the problem.
So you set up your experiment in the lab with the camera and everything?
Yes.
Wouldn't that diamond have a different frequency than the actual diamond wafer as the experiment was?
It would. The piece of glass we were using is larger, and obviously it's not going to be the exact same mass and everything. However, this is helping us get a basic idea of what to do. And using equations and such, we can translate the math of what our results with this piece of glass to the results of the diamond.
Why, I was confused by the part why you couldn't put it in a frame or at least like attach more tungsten wires to minimize that movement.
Well, we essentially want the diamond to be in a vacuum. We don't want electrons to be hitting a frame that's directly around it, and I think maybe Dr. Jones could.
Well, if the electrons, if it's mounted on a frame, the electrons are going to hit the atom of the frame. It's going to throw off all sorts of carbon particles. We don't want those. So we suspend it in a frame with a minimal amount of material around it and a lot of space, so that if any electrons actually miss the diamond, they're just going to go through the space and not hit anything. We want to try and minimize the amount of garbage particles we put on hitting through the frame.
Thank you, Chris.
So you can like another 4 or 5.
Yeah, increases the chances. Well, all right, thank you.